All right, so I'll slowly start to introduce our next speaker. That's Jose Lado here from Aalto University. And Jose will tell us about engineering topological non-Hermitian quantum and photonic matter with modulated losses. So are you ready, Jose?
Yeah.
All right, okay, so please.
Yeah, great. Thanks a lot, Christian, for the very kind introduction. I'd like to start by thanking Anton and Florian for putting together this absolutely wonderful workshop. So today I'd like to tell you a bit about non-Hermitian systems. In particular, these are systems that are open to an environment and how we can use this openness to an environment as a driving force to engineering topological matter. And so the background of this is just the whole field of topology. So as you know, topological insulators started almost 2 decades ago, and now we have many, many instances of topological states of matter. We have the quantum Hall state that was, of course, known for a very long time. Now we have, let's say, topological metals, such as Weyl semimetals and nodal Leiden semimetals. We have topological crystal insulators, quantum spin Hall insulators, and we even have topological superconductors. The common framework of all these topological states of matter is that, first, they are single particle states of matter. We can understand this physics just from single particle physics. And the second one is that all these materials are close to an environment, or they should be close to an environment. So from this perspective, there are two directions that, in a way, they are a new venue for topological matter. The first one is what happens if we have simultaneously topology and many-body interactions. This is maybe one of the most important questions now in fundamental condensed matter physics, and there are now very exciting experiments bringing together these two ideas, such as fractional Chern insulators. And then the second one is what happens if we actually have systems open to an environment, and whether if this openness to an environment is actually a driving force for topology. And this is also a direction that started a few years ago that is known now as non-Hermitian topology. And so today, I will try to bring together these two ideas and actually show you that these are not disjoint ideas, but that there are actual some systems that can be seen both from the perspective of many-body interactions or from the perspective of non-Hermitian topology. And so the whole idea is that in many-body systems, we can have entangled states that do not have any counterpart in single particle systems. And there are many well-known examples, such as quantum spin liquids that appear in quantum magnets that show long-range entanglement, fractional quantum matter, such as fractional quantum Hall state and fractional Chern insulators, and even some states that we have not seen in experiments so far, but we may see in experiments in the next few years, such as parafermions or Fibonacci anyons. In the case of non-Hermitian systems, we can actually see some phenomena that is, in a way, forbidden in closed systems. We can see, for example, excitations that are protected in systems that are topologically trivial from the point of view of Hermitian topology, and we can see even more exotic things, such as a non-Hermitian skin effect in non-Hermitian systems. So this is states that start localizing in some parts of the system and not others. And so the idea for today is that I will show you several examples that bring together these two ideas, and they actually have one thing in common, which is that all these phenomena arises just from modulating the coupling to an environment. You don't need any exotic non-reciprocity or many other things that are needed for non-Hermitian physics, but it's just modulating the coupling. And I'll show you several examples. I'll show you how we can actually get criticality in topological states just by modulating coupling to an environment. We can actually realize this experimentally using integrated silicon photonics. That's the second thing that I will tell you. And then I will show you how we can actually compute many-body excitations and many-body dynamical correlators in generic non-Hermitian interacting models. And finally, I'll show you an example of a topological state of matter that is a many-body topological state, but at the same time, it is also a non-Hermitian topological state. And before going to the physics part, let me emphasize that everything that I'm going to tell you today would not have been possible without the help and with the wonderful work of many people here. In particular, Elizabeth Honway and Andrea, and I mean that led all the work on the theory of non-Hermitian criticality and the experimental realization. Then Honway, Wanse, and Sina, and Elizabeth also that did all the work on many-body interactions and non-Hermiticity arising from many-body interactions. Okay, so let me start with a very simple question. So how does non-Hermiticity appear in a Hamiltonian? And more concretely, how does it appear in an actual experiment? We are usually taught, at least during our bachelor's, that systems are Hermitian, but of course, we are interested in non-Hermitian systems. So there are many ways of understanding this, and let me just show you one that many of you are aware, but just for the sake of everybody being on the same page. So imagine that you have a certain resonator. So this is, for example, a resonator H0. This can be a quantum dot, it can be a qubit, it can be anything that has a single mode. And now you take this single mode resonator and you couple it to an environment, that it's this yellow environment over here. From the point of view of the Green's function of the system, you can think that the whole dynamics of the system is described by the Hamiltonian of the quantum dot, the Hamiltonian of the environment, and a coupling between them. And just by using the conventional Dyson equation, you can show that the effective Green's function of the quantum dot depends in a way of the Green's function of your environment and the coupling to the environment, and this is what we call the Dyson equation that has the self-energy over there. The most important point is that this is a relatively generic idea, and the self-energy has two contributions. One contribution that is Hermitian, and this contribution renormalizes your coupling, so it may renormalize your Fermi velocity, it may renormalize your on-site energies, you can even think that this is some sort of Stark effect and so forth. And then there's another part that is non-Hermitian, and this non-Hermitian part effectively creates a non-Hermitian term in an effective Hamiltonian. So every time that we talk about non-Hermitian Hamiltonians, we are effectively having this idea in mind. We are working with an effective description of the system, with an effective description that is associated with the Green's function of the system, which is, of course, not the true full description of the system. But you will see that for many practical purposes, this is actually good enough, and we can predict many interesting phenomena in these systems. Okay, so in general, we have a Hamiltonian that has a Hermitian part and a non-Hermitian part. And the non-Hermitian part, it is, in the simplest case, a imaginary on-site energy. And now you can think that if you play this game not with one resonator or one quantum dot, but with many of them, you can actually couple different environments to each one of your dots or each one of your resonators. And you can actually have an imaginary part of your self-energy that it's bigger for one parts of the system and smaller for other parts of the system. So you can have big losses in one part, small losses in the other part, and so forth. And the idea for today is that we are going to just exploit this idea. We are going to consider that we couple the different parts of the system in this different modulated way, and this is going to be the driving force for all the topological states that we will see. Okay, so let's start with the first one. And this is a very minimal model that shows you that just by modulating these losses in a system, you can actually get all sorts of topological states in criticality. And this is, of course, the work by Elizabeth together with Hongwei and Andrea. Okay, so the idea is relatively simple. So imagine that you have a one-dimensional chain of these resonators. This can be a one-dimensional chain of quantum dots, one-dimensional chain of optical resonators, and they will be optical resonators later on. Now what we are going to do is we are going to consider that the resonators are coupled, so there's an effective hopping, and then there's a on-site energy that it's imaginary, that it's our loss. It's our site-dependent coupling to an environment. And we can modulate this loss in many ways. The way in which we choose to modulate it is in this sine form. So we are going to have a frequency of this modulation. This is a spatial frequency of the modulation. There will be an amplitude of the modulation that it's VI, and then there's a phase shift of the modulation. For many of you, this Hamiltonian will look relatively familiar, and this is the Hamiltonian of the Aubry-André-Harper model, but in imaginary form. This is a Hamiltonian that is very well known for having topological physics, at least in its Hermitian form, but this is the non-Hermitian one. So now the whole trick is the following. So if you choose a very specific case, so you take some modulation frequency of 1/4, so unit cell of 4 sites, and now you look at the spectra as a function of the strength of the non-hermiticity, the strength of your losses, what you actually observe is that a gap opens up and a single state appears inside the gap. This state is a state that is localized on the edges of your system, and this is a topological state of matter. So this is a system that has a gap in the bulk, gapless edge excitations, and they simply arise because you decided to modulate the losses on your system. There's nothing else in this Hamiltonian. And then you can see that, of course, as you make your loss modulation stronger and stronger, then the edge state localizes more and more at the edge of the system. This is not just a special case of the Hamiltonian. If you start looking at this Hamiltonian as a function of the frequency of the modulation, you will see that actually these edge states exist all over the spectra. So you have a continuous family of topological states, that show gapless excitations and some spectral gap, that they are actually not even periodic. They don't even have a unit cell. So this is, in general, a quasi-periodic non-Hermitian topological insulator. All these red states over there are edge states, and you see that they exist for all frequencies, and the blue states are the bulk states. And you can see that these edge states are actually pumping as a function of the phase shift that you have in the Hamiltonian. And in the case of the 1/4, you see that they appear just as flat bands as a function of the phase shift, and then for other frequency modulations, they start to disperse, but they still exist. And this is very similar to what happens in the O'Brien-Harper model, in particular when you map it to a quantum Hall state. Okay, something very important of topological states is that they must be robust. They should not depend on details of the Hamiltonian, they should not depend on disorder. And in particular, in the case of these non-Hermitian topological states, what we actually see is that they are very robust to any perturbation in the loss of the system. So the loss doesn't have to be perfect, it can have disorder in the loss, which is the picture on the right. But if you have disorder in the on-site energies, so disorder in the resonant frequency of your dots, then you start losing your edge states. So the topological protection is not absolute. You have protection against disorder in the loss, but not disorder in the resonance frequencies. Okay, so now let me show you one more step. So we can actually generalize this modulated model, and we can have modulations not only in the loss, but also in the resonance frequency. And the interest of this model is that this is a generalized model that in one case gives rise to the model that I showed you before, in the other case gives rise to the Hermitian version that it's very well known, and in the middle we have something else. And so the important point is that as you start changing the strength of the loss modulation, you actually get a localization-delocalization transition. So when the losses when the strength of the loss is small, your states are delocalized. They are effectively plane waves in your system. When the loss is very strong, you get localized states. And in the middle, you get a critical point. And more specifically, you get a critical point at all energies simultaneously. And this is something that appears in the generic modulated model. You can modulate the losses, you can modulate the resonance frequency, and then you see that there's always a critical point that brings you from an extended state to a localized state. So this model alone has very interesting phenomena, has topological states, has criticality, it has transitions from localized to extended. So now let us move on to see actually this experimentally. And this is the experiment that was done in the group of Andrea Blanco Redondo. Okay, so what we are going to do is we are going to realize this with optical resonators. And in particular, this is done with an integrated silicon photonics platform. So we effectively have a grid of hexagons, and in each hexagon, we effectively realize a single resonator. And the most important deal of this platform is that you can actually tune the coupling between your resonators, you can tune the resonant frequency of your resonators, and you can also tune the losses of your resonators. And you can inject light in the one that you want and measure light in the other one that you want. So in a way, it is kind of the dream for realizing, let's say, minimal models of non-Hermitian systems. And so as a starting point, we will realize this model. So the topological model that has these modes at the edge. And we are going to take a system that has 8 sites. And so on the left, you see the experiment. On the right, you see the theory. And this is, of course, a relatively short system. So let's say the edge states are not fully localized in the edge. But what you can clearly see is that we have a very bright spot at the beginning. And at the end, in the experiment, if we do the simulation with the experimental parameters, we get effectively the same. And then there's a small overlap in the bulk of the system. We can, let's say, look at the wave functions themselves more concretely, and this is something that we can do also experimentally, just by measuring the different resonators independently, and you see that effectively the profile of the two modes, the bonding and anti-bonding between the two edge states are effectively the same between theory and experiment. So this effectively tells you that this platform allows you to very much realize this minimal model of a non-Hermitian topological state that we discussed before. Of course, there's another, perhaps more interesting case, right? Which is the case in which the modulation frequency is not commensurate with the lattice. The case in which we have a quasi-periodic non-Hermitian system or a non-Hermitian quasi-crystal. And in this case, of course, the topological states would appear, especially when your system is large enough, but we can try to do a minimal version of this. And if we use this non-commensurate modulation and we compare our experiment with the theory, we observe that we effectively get very much comparable spectra. So on the left, you see the experiment. On the right, you see the theory. This is, of course, not a system not large enough to show criticality, but it shows you that you can actually go to this quasi-periodic regime and emulate these quasi-periodic non-Hermitian Hamiltonians also with this platform. And then one last important point is to see if these edge modes, these topological edge modes, show the same robustness as the one that it is expected theoretically. And this is something that we can also do experimentally. We can take the topological state and start adding disorder in the resonance frequencies and the losses. If we add disorder in the resonance frequency, we see that the edge mode is very robust, which is what we expected from the theory side. And if we start adding disorder in the resonance frequencies, we see that the edge mode shifts quite a bit, which is also what we expected from a theory side. So in practice, this photonics platform realizes all the phenomena that we were expecting from a theory side. So it is a very promising platform to start looking at even more exotic non-Hermitian phenomena. OK, good. So this is everything that I wanted to tell you about single particle physics. Now, it is a good time to start moving towards many-body physics. So the question that I want to answer now is, how can we understand systems that have simultaneously non-Hermitian losses and many-body interaction? So far, our photonics platform was effectively a single particle system. And this is the work of Wanse and Fei. OK, so once you are in a many-body setting, you can no longer just look at the eigenstates of your system, because the eigenstates grow exponentially with the system size. So you need to start looking at some other object that is more physically meaningful, and in particular that is more related with the observable that you are interested in. And this object is the so-called dynamical spectral function. And the way of understanding it is that, for example, if you have a fermionic or bosonic system, what you actually want to see is, I take my initial state, that is the ground state, I create an excitation, and when I create an excitation, do I have an excited state that has a certain energy? If yes, then I see something. If no, I don't see anything. And that's the meaning of the formula on top, and you can define it analogously for spin models. So this looks simple enough, but of course there are two challenges when you deal with non-Hermitian many-body systems. The first challenge is that the spectra of your non-Hermitian model is no longer real. So you no longer have just a single frequency axis, but you actually need to think that your dynamical correlators are defined in the whole complex plane. So frequency can be real, frequency can be imaginary, and you need to find a proper definition of this. And then the second challenge is actually perhaps even the most important one, which is that many-body systems are by themselves very hard to solve, and they are very hard because the system sizes that you need to solve in terms of algebra increase exponentially with the number of sites. So even if you have 30 sites, then you effectively go to system sizes that you cannot solve exactly. And so to deal with this challenge, what one can use is something called tensor networks or matrix product states. And the whole idea of this is that when you are solving a quantum many-body system, maybe you don't need to store the whole wave function by itself, so you don't need to store every single coefficient of the wave function. Maybe the only thing that you actually need is to store a compressed version of that many-body wave function. And this technique that it's called tensor networks effectively allows you to do this in a systematic way. So you replace a conventional wave function that is a set of numbers with many, many indexes with a matrix product state representation. And from a pictorial point of view, you can just think that this is like an image compression algorithm. Your original wave function is a very high quality image. The new wave function is a lower quality image, but that still retains all the important information that you needed to know about the wave function. And maybe the most important thing about these tensor networks is that, in general, they allow you to do algebra in exponentially large spaces. You not only can deal with vectors, you can also deal with matrices, and you can apply these matrices, called matrix product operators, to states. You can sum them, you can multiply MPOs, and so forth. And effectively, this is the whole machinery that we need in order to compute these non-Hermitian dynamical correlators. OK, so let me show you a few examples of how we do this. So let's imagine that you have a generic interacting non-Hermitian model. You can think that it's a spin chain with some imaginary magnetic fields, or an electronic model that has imaginary on-site energies. They are effectively equivalent by a Jordan-Wigner transformation. And what you're interested in is in computing the local density of states, or the particle dynamical spectral function. And so what you effectively do is you define a non-Hermitian version of the dynamical correlator. This is maybe a bit intimidating formula, but the important thing of this is that, first, it depends on the real part of the frequency and the imaginary part of the frequency. It depends on right eigenvectors and left eigenvectors. And in practice, it reduces to the conventional density of states or dynamical spectral function once your Hamiltonian is Hermitian and you integrate over one axis. Let me show you the results. And even though I didn't tell you exactly how the method works, what is important is what the method allows you to actually compute. And so this is the case of a topological system. And the idea is that we have a finite-size system in which we start increasing the topological gap. And as we increase the topological gap, we expect that edge states are going to appear, and edge states are going to give rise to a topological degeneracy in the dynamical correlator. And this is effectively what you see. As you make the system bigger and bigger, you see that when the system, as you make the gap bigger and bigger, you see that once the gap is big enough to confine the edge modes, you effectively get a degeneracy in the real part of the frequency. And of course, what's most important is that as you make the gap bigger and bigger, edge states start to appear in your Hamiltonian. So when the topological gap is small, the edge states are hybridized very much. But then you make the system bigger, they hybridize less. And then once the system is big enough, you effectively get zero modes. And of course, this method can be used for very big systems. You can do systems with, for example, 24 qubits. You can do systems with 40, 50 qubits. And all this can be done in a conventional laptop. And in all cases, you can see your topological edge modes. OK, so far I was talking all the time about systems that have non-Hermiticity by construction in the Hamiltonian, right? And we argue that this non-Hermiticity by construction comes from a coupling to an environment. Maybe an important question is if non-Hermitian physics is also relevant when you don't have a coupling to the environment, when you have a system that is closed, and somehow the system itself is its own bath. And this is what I'm going to tell you now. And this is the work of Sina Wanse and Elizabeth. What we are going to focus on now is on a Kondo lattice. This is a relatively simple quantum many-body model. You have a system where you have electrons that they do not interact. They are absolutely free. This is the chain that you have in the bottom. And then you have spins on top. And these spins are coupled to your bath. From the point of view of the ground state, then the type of ground state that you expect is a state in which each spin is screened by an electron in your bath and forms a singlet, and all these singlets become coherent due to the coupling within the metal. And this is a very well-known Hamiltonian. This is the Hamiltonian of a Kondo lattice, and you can think that this is almost a minimal one-dimensional Kondo lattice, with the caveat that we don't have spins on every single side of the chain. We decide to put spins just on some sides, but not on the others. OK, so the Hamiltonian of this system is relatively simple. We have the kinetic energy of our electrons that are non-interacting, and then there's a Kondo coupling to our sides. And that's all. There's no coupling to an environment whatsoever. This is a completely closed system. So now what we do is we can start solving this system. And in particular, we solve this type of Hamiltonian with tensor networks with a methodology that is relatively similar to the one that I told you before, just the Hermitian version. And what you actually observe is that if you compute the density of states of this system, you suddenly see that H states appear in this system. There's no coupling to an environment. This is just a condo lattice that is somehow modulated. And these H states are actually fairly robust. You can start putting all sorts of disorder in the hopping, disorder in the on-site energies, and so forth. And the H states, they remain there. They don't change. So somehow we know that these H states, they must be topological because they are robust to our perturbations. The question is, why are they topological and why are they appearing here? Let me emphasize that this is a many-body state of matter, right? We don't have single particle states. This is a condo system in which the only thing that we have is a ground state wave function that we solve with tensor networks. And so one can do two different things. The first one is one can think. And after a little bit of thinking, you can actually realize that from the point of view of an effective Hamiltonian, you can actually transform a condo lattice Hamiltonian onto a non-Hermitian Hamiltonian. And the idea is relatively simple. So imagine that you want to integrate out the spins. You want to find an effective Hamiltonian where the spin degree of freedom has been integrated out, and the only thing that you have is degrees of freedom for your electron gas. You can use something similar to a Dyson equation. Now it's an interacting one. And at the end of the day, what you actually get is that the spins in your condo lattice give rise to a self-energy for your electrons. This is an interacting self-energy as it appears in many-body physics. Now, the whole deal is that this interacting self-energy, it effectively acts as an imaginary on-site energy in your former spin sites. And one way of thinking about this is that if you are in an electron that is propagating on the electron lattice, when you encounter a spin, you have a certain probability of stopping being an electron, of in a way disappearing, and disappearing into a spin singlet. And this possibility of disappearing is what this imaginary on-site energy effectively gives rise in the effective Hamiltonian. And then, of course, you can even integrate out this imaginary on-site energy in the spin sites and end up with a local loss in your chain. So after doing this mapping, you can actually realize that the condo lattice is acting as a bath to itself. The condo sites are creating, in a way, a bath to the electron sites, and this is creating an effective non-Hermitian model. And you can sort of convince yourself that this picture makes sense just by comparing the spectral functions of the two models, of the full model that you compute with tensor networks, of the effective model that you compute with the effective non-Hermitian single particle state, and you see that everything looks very similar, both H states and excited states. Of course, one important question is if this is just something that happened out of luck, or if there's some deeper reason for this to happen. And you can actually show that the topological invariant of the non-Hermitian effective model is actually the same as the true topological invariant of the many-body model. And in particular, for the condo lattice model, one can compute the topological invariant using something called a correlation pumping matrix. So the idea is that you start with your many-body Hamiltonian, you compute a correlation matrix that depends on the winding of your initial Hamiltonian, and the winding of this correlation matrix allows you to compute a topological invariant. The important point of this method is that this is effectively the same as the single particle topological invariant if you didn't have interactions, but this is also a meaningful object to compute in a many-body setting. And effectively, once you compute this topological invariant, you see that you get the same one as for the non-Hermitian model. And so, in short, this is everything that I wanted to tell you today. So if I can ask you to remember something, please remember that non-Hermitian topological modes can appear in engineered systems where we control the effective local losses, and that we can probe the H states. And this can appear both in electronic systems and in photonic systems. And thank you so much for your attention.
All right, thank you very much, Jose. And we have time for questions or comments from the audience. Anton? Yeah.
Thanks, Jose. Nice talk. I was wondering, at the beginning you mentioned to the first part of your talk where you modulated the losses. I didn't quite grasp, what's the modulation depth for the loss?
Yeah, so here, right? So the modulation strength, so how much the losses change from one to the other, is the VI.
Yeah, but relatively to see the effect in the experiment.
So you need, so maybe this is the best plot to look at this. So you need to see something, you need something on the order of the coupling between your resonators. If the loss is very small in comparison with the coupling, then the topological gaps that you get are very small. If it is too large, everything is dominated by the loss in a way. So the good regime is this one over here. And this is the regime also where you get criticality.
Yeah. And did you see these experimentally with your collaborators already or not yet?
Sorry,
experimentally, did you see this effect experimentally with your collaborators? Or?
Yeah, so this regime, yes, we saw it.
Okay.
Yeah, in this regime we can also explore, but it's of course much harder to measure anything in the bulk in that regime because everything is dominated by loss in that regime. Yeah. So all our experiments are effectively in this regime.
Okay, thanks.
Other questions? Yeah, there's one here.
Thank you for your talk. Maybe my question will sound naive or strange. I'm not really familiar with the concepts. Is it important that your spin only captures the electron but doesn't give it back?
Yeah, that's a very good question. So the local spin is, in a way, it's entangling the electron path. So you can actually think that the electron is truly never jumping to the spin site, but it's forming a singlet with the spin site. And you can think that a creation of singlets and breaking of singlets is dynamically happening all the time. So what is important is that this Kondo coupling, it effectively takes an electron that is propagating without caring about anybody else and entangles it with a spin. And of course, after some time, this entanglement may be broken.
Okay, so it's kind of also that probably the closest to that spin electrons will get entangled.
Yeah, absolutely. So the coupling is local. So when you pass close to the spin is when the spins get entangled.
And you say that it's kind of entangled, it's jumping back and forth. Are we looking? So here you're looking at the steady state kind of solutions, but then the jumping back and forth. What is a steady state then, right?
Yeah, so what we were looking in that case was at the ground state of the system. So you can think that from a dynamical point of view, this forming and breaking of singlets is happening all the time. But then you can say, okay, this is a quantum many-body Hamiltonian that is effectively time independent. What is my actual many-body ground state? The many-body ground state is the electrons, all the electrons entangled with all the spins in a static way. But of course, if you started making perturbations, you could see that singlets start breaking and forming again. But from the point of view of our calculations, everything is static.
Okay. All right, there's a question here.
I was wondering if some of your concepts, not all of them, but some of your concepts could be mapped to time and have time situations where you have, well, the analogous to topological edge states like, I don't know, subharmonic generation or many-body localization or something. Can you map, not on a one-to-one, but what are the trends for time?
Yeah, that's a very good point. And absolutely, yes. So many of the non-Hermitian phenomena that appears, they appear actually in dynamical settings. So in settings in which you actually create excitations in the system and you are studying the effective time-dependent stage. So everything, so the non-Hermitic cases that I mentioned here, they are just a very small subset of all the non-Hermitian things that may happen. These ones are relatively static in a sense that you can think that it's just a steady state, but there's lots of non-Hermiticity that can appear in a dynamical case. Yeah.
All right, a question in the back.
My question is very short. As far as I understand, you are considering the local approach to relaxation process in your open quantum system. What would happen if you consider the global approach, where you Hermitian part changes your non-Hermitian part?
Yeah, so I guess that your question is how one could treat this from a more, let's say, Liouvillean point of view, or is it different?
My question is that if you consider this not from point of view of local approach to relaxation operators, but from global approach to relaxation operators, actually, your interaction between the sites, go back to, the interaction between the sites n and plus one will change your relaxation process, and you would have non-Hermitian jumps between the sites. How will it change the whole picture?
Yeah, that's a very good point. So, for example, if you had, let's say, non-reciprocal hoppings, then this would promote skin effect. And this is the type of non-Hermitian term that can appear due to this process. So the reason why we didn't consider this in the model is because it also doesn't appear naturally in that experimental platform. There are other photonics platforms in which one can have these other additional non-Hermitian terms. But in this case, it doesn't appear.
I argue that it might appear because your dissipation rate is as high as your interaction term between the sides.
Yeah,
so the global approach might be the right way to consider this kind of stuff.
Yeah, so I mean, you can have, let's say, non-local losses, if you wish, but you may, I mean, at least we didn't see anything that was consistent with a non-reciprocal.
It's not non-local losses, it's local or global approach to the relaxation process.
Yeah.
You see, the whole relaxation process takes into account the eigenstates of your system. And all the jumps, all the relaxation process goes between these eigenstates. And if you introduce the high interaction between different sides, your eigenstates changing your relaxation process. So instead of A plus dagger A, you would have operator, let's say, call it B or whatever, which is eigenoperator of the system. So it will change your relaxation dynamics in your system.
Yeah, all right, so like an additional term. So I would say that we didn't include additional terms because we didn't have an experimental reason for doing it, or at least we didn't see anything that points to this existing. So with this Hamiltonian, we effectively could account for everything.
You have some discrepancy between theory and experiment, and this might be due to like this local approach instead of correct global approach.
I mean, we have some discrepancies, but of course there are other terms. Yeah.
Okay, yeah, so
Very
we'll
nice stuff.
continue discussion at lunch. I will have one last question, and perhaps Jose. So, and since you look at these non-Hermitian Hamiltonians, I imagine you also think about exceptional points. So do they have some importance here?
Yeah, absolutely. That's a very good point. And in particular, this type of model has many exceptional points. And it turns out that there's some correlation between exceptional points and localization-delocalization transitions. So the mapping is not one-to-one, but it seems that every time that you have an exceptional point, it is possible that you may have a delocalization transition. This is, of course, something that will be very interesting to look at in the system.
All right. Okay, so thank you. So let's thank Jose again.